In this video, I'm going to work a few problems that will help you a lot, I think, on the homework and probably help you a lot on the test as well. You want to be pretty comfortable with these. One type of problem is, how do we find an index of refraction? The speed of light in ethyl alcohol is 2.2 times 10 to the 8th meters per second. What is the index of refraction? Well, by definition, the index of refraction is the ratio of the speed of light in a vacuum to the speed of light in the substance. The speed of light in a vacuum is always 3.00 times 10 to the 8th meters per second. Okay. For ethyl alcohol, the speed of light is 2.2 times 10 to the 8th meters per second. You'll notice some things. You'll notice the meters per second completely cancels out. You also probably can notice that the 10 to the 8th actually completely cancels out. So if you want to do, all you really have to do is 3 divided by 2.2. If you do decide to use the whole number, be sure that it's all of this divided by all of this. Parentheses will help you get the right answer. So I just need to do 3.00 divided by 2.2 because I know that cancels with that and makes 1. I know the units cancel. It comes out to be about 1.36. So index of refraction, speed of light divided by the speed in the substance. Okay. Let's do another example. What is the speed of light in quartz if N is equal to 1.5 for quartz? We know that the index of refraction is equal to C over D. If I want to know V, which is what I'm looking for, I know the index of refraction, I know C. It may help you to think that formula rearranges to be that V is equal to C divided by N. So there's two ways that these questions are answered sometimes. One way is to just leave the C in the answer. V is equal to C over 1.5. If I put a 1 here, that's 1C. If I do 1 divided by 1.5, I get 0.67. So it is equal to 0.67 C. That's the answer in terms of C. And I know that was on some, I want to say there's probably a question that has the answer like that on the homework quiz. where you just say, okay, I just need to do 1 divided by the index of refraction, and that will tell me what fraction of C it is. The other way is to just go ahead and put C in. If I put C in, C is 3.00 times 10 to the 8th meters per second. The index of refraction is 1.5. Well, if I divide 3 times 10 to the 8th by 1.5, I get 2.00 times 10 to the 8th meters per second. Notice that's exactly 2/3 of the speed of light, which is what 0.67 is. It's 2/3 of the speed of light. Okay, so that's one type of problem. The other types of problems are going to use a different formula. So this is going to be a really important formula, whether it's written like this or like this. The other really important formula that we need to look at is an old one for waves. Light is an electromagnetic wave. So our other formula that we've used for a long time with waves is that V equals the frequency times the wavelength. Really important formula. What is the frequency of light with a wavelength of 590 nanometers? Okay. We measure wavelengths of light frequently in nanometers. You may or may not remember that light, visible light, the color that you see, goes from 400 to 700 nanometers. This is violet. It has the shortest wavelength. This is red. It has the longest wavelength. So nanometers are something we need to be comfortable with. 590 nanometers is the same as saying 590 times 10 to the negative 9 meters. Nano just means negative 9. Okay, so we know the wavelength. The assumption in this problem, if they do not tell you that you're traveling in water or you're traveling through quartz, is that you are traveling through air. And the speed of light in air, of course, is 3 times 10 to the 8th. So we know that V in this case is the same thing as C, 3.00 times 10 to the 8th meters per second. So if we use our formula V equals F lambda, we get the speed of light, 300 times 10 to the 8th meters per second, I don't guess I need my parentheses yet, equals the frequency times the wavelength. The wavelength is 590 times 10 to the negative 9. If I'm going to solve for the frequency, I'm going to have to divide by 590 times 10 to the negative 9, that's hertz per second on both sides. That, of course, cancels, and we just get F. So when I do my math here, be very, very careful that you divide by all of this. And when you do, you're going to get an answer of about 5.1 times 10 to the 14th hertz. Anytime you're talking about visible light, the frequency is going to be around 10 to the 14th hertz, okay? Because it's going to be this 3 times 10 to the 8th divided by a number somewhere between 400 and 700 nanometers. And it's always going to give you one that is about that size. Okay, let's do another example with that same formula. Suppose that we have orange light, kind of an unusual color. Nope. Yep, we'll go ahead and do it. That's got a wavelength . 650 nanometers in water. Light travels at 2.25 times 10 to the 8th meters per second in water. Find the frequency. So this problem is almost exactly like the problem that we just did, except they told us we were not traveling through air. So the speed of light is not 3 times 10 to the 8th. Since it is in water, it's traveling more slowly, but it's the same formula. 2.25 times 10 to the 8th meters per second. That's the speed of the light. We don't know the frequency, but we do know that the wavelength is 650 nanometers. 650 times 10 to the negative 9. So to solve, I'm going to do 2.25 times 10 to the 8th divided by 650 times 10 to the negative 9. Again, be really careful with your scientific notation. I expect my answer to be close to 10 to the 14th. Now, it's not traveling through air, but I still feel like it'll be in that neighborhood. 2.25 times 10 to the 8th divided by, I'm going to put parentheses, 650 times 10 to the negative 9. And my answer came out to be 3.46 times 10 to the 14th hertz. So that makes me feel good. The frequency's about right. Now, one of the things I want to remind you of, just because we're kind of doing these problems, when light travels from one medium to another, the frequency will not change. When light travels to a new medium, its frequency will not change. However, two things will. When it goes into new mediums, the speed changes, and therefore the wavelength changes. But that number stays the same. If the speed increases, the wavelength gets larger. When it slows down, the wavelength gets smaller. So what it tends to look like is, let's suppose you have a wave in air. Well, it travels very, very fast in air, and then you go into water. So when it's going very fast, the wavelength may look like this, but when it slows down, it gets bunched up like this. The wavelength will get smaller, but the frequency will stay the same. So frequency stays the same. Generally, the amplitude will stay the same. However, the speed and the wavelength will change. Let's do one more problem, and we'll finish our problem solving. is a particular green light, has a frequency, I'll just put F, that equals 5.7 times 10 to the 14th hertz. What is its wavelength? In air or in water? In water, we need to remember it goes this fast. Okay, let's do air first. In air, the velocity is c, or 3.00 times 10 to the 8th meters per second. Light travels at the speed of light in a vacuum, but it's really the same speed in air. So our formula is V equals F lambda. So if it's going at the speed of light and its frequency is 5.7 times 10 to the 14th times lambda. I need to divide all of this by 5.7 times 10 to the 14th. I need to be really careful to divide by that correctly. I think it should come out to be a few hundred nanometers. So let's see, 3 times 10 to the 8th divided by 5.7 times 10 to the 14th. It comes out to be 5.26 times 10 to the negative 7 meters. And that is the correct answer. Now, that doesn't say nanometers, and that's fine. It doesn't need to say nanometers. But if I wanted to write that, that's the same as 526 nanometers. So when you're doing these problems with light, expect your wavelengths to be in terms of 10 to the negative 7. Or they may give it to you as a few hundred nanometers, 400 to 700 nanometers. But when you work it out, you're probably going to get 10 to the negative 7 for wavelengths. You're going to get 10 to the 14th for frequencies. That's going to help you know if you're doing it right. Okay, so if it's traveling through air, this is its wavelength. I'm going to write it up here. It's 5.26 times 10 to the negative 7 meters. Now, when it travels in water, I think that wavelength's going to get smaller. It's going to slow down. So let's see what happens in water. For water, we use V equal F lambda. Only now the speed is 2.25 times 10 to the 8th meters per second. That's how fast it travels in the water. So we're doing water this time. The frequency of the light does not change. Frequency does not change when you change medium. So 5.7 times 10 to the 14th hertz times the wavelength. So I need to get this wavelength by itself, so it's this divided by this. And that's going to give me my new wavelength. So very carefully, 2.25 times 10 to the 8th power divided by, and I'm going to put parentheses on this. I don't want to get a wrong answer. 5.7 times 10 to the 14th. And now the wavelength comes out to be 3.95 times 10 to the negative 7 meters. So definitely the right size, but notice it got smaller. That's exactly what we said. When it slows down, the wavelength gets smaller. If this is smaller, this is smaller. That stays the same. Okay, I think that's going to help you a lot with the problems on the homework quiz. So look over these, make sure you understand them. There's really only a couple formulas. And I will try to post that formula sheet online for you also. So you should be good on chapter 19.